So in the last class, I didn't really do satisfactorily something about some example on connectedness. So I will do it again. I will not recall the proofs, things which we have already proved. So one thing is this. We talked about this example. So this is X, and this is a example for a set being path connected, but not set being connected, but not path connected. Then you can take X in this half open, closed interval. Then E closure will be E union this. It is not important for us, but you can verify it. It will be part of the proof. It will be there in the it will be contained in the proof. Okay. So we want to prove that E closure. You can take a subset between E and which contains E and contained in E closure also. The same proof will work for that also. But we want to prove it for E closure because it looks like something disconnected or something. Because in the earlier example, some sort of comb example, it was like that. I took a point somewhere, but if I had taken the zero, the origin, then it will be connected. It will be path connected. So this is the example which is different from that. So okay. So we want to prove that this is connected because E is connected and E is just a curve, so it is connected. So E closure is connected, which we have proved. So E is connected. Okay. Claim is E is not E closure. E is connected, so E closure is also connected. Okay. So the claim is E closure is not path connected. Suppose it is path connected. Then suppose this point 0, 0, which is in the E closure, of course, 0, 0, and you take the 1 sin 1 are connected by a curve. Connected by some gamma. Okay. Then we want to get a contradiction. So we defined T naught to be infimum of all those T such that gamma T is takes values in, the gamma T, the image is contained in E closure, gamma T is in E. Okay, we called it T naught. Then we proved that because this set is closed, for anything less than T naught, it is in that set is closed, T naught, gamma of T naught will be in that set, in this set, cross minus 1, 1. This thing we proved. So this implies gamma of T naught is equal to some 0, y naught. For some y naught in this interval minus 1, 1. Okay. So we want to get a contradiction. So the thing is this: for delta greater than 0, there exists a T in this interval, closed interval, T prime, such that gamma, such that gamma of T is in EF. By the definition of the infimum. This is the infimum of such thing. So if you increase it something, there should be something in that. That's the definition of infimum. Okay. So this implies to take the coordinate projection. Px is the projection onto x-axis. This is projection onto x-axis. Similarly, the projection onto y-axis is py. You take the px and you apply it on this gamma t. This particular T, maybe call it T prime or something. Okay, so that it's not very easy. So the Px of gamma T prime is in E. And not in E. It's going to look like gamma T is going to be something in this 0, 1, right? Okay, something in something in 0, 1. Maybe. So maybe it's some x in 0, 1. Okay, something. We call it is equal to some theta, which is in 0. Sorry. Yeah, this is okay. Call it theta or x prime in 0, 1. It is some value in 0, 1. Okay. On the other hand, Px of gamma of T naught is going to be 0 by the definition, of course. Px of T naught. is 0. But then this gamma is a continuous function. Gamma of T naught is this, gamma of, Px is a real valued function. Px composed with gamma is a function from 0, 1 to x-axis. So it takes some 0, 1 to real number. So we can use the intermediate value theorem. That's what I missed last time. Okay, by intermediate value theorem. Or the connectedness or something, intermediate value theorem. Or use the connectedness or something. All values between T naught, all values from 0 to x naught should be taken by something, by some T naught to T prime, right? All values should be attained. It may go out of the set, but it should be attained. Okay. So, this is true for all delta. Okay, let me say, for all delta, you have a T prime less than that delta, such that all values between 0 to the corresponding to T, there will be some value. So this will imply that there exists a Tn going to T naught. No, Tn need not go to 0. Sorry, there exists a Tn such that gamma of Tn Tx will go to 0. And Px of gamma of Tn, Px of gamma of Tn can be chosen anywhere, anything. Right? All I am saying is that clear? Should I write? Should I make it more clear? I am saying that for all delta, any delta, you increase it between T naught to T naught plus delta. Okay? There exists something here, such that less than that, which you can choose any value, and you will take the any value from 0 to x prime. 0 to x prime, any value. So all I am claiming to say is the following. So there exists a sequence Tn in this T naught to 1 or something, T naught to 1, okay, such that gamma of Tn, let me write it and it will be clear. Px of Tn, okay, goes to 0. No, gamma, I don't want it to go to 0. I want it to be a particular value, I'm sorry. Again and again, make a mistake. Such that 2 pi n plus theta. Okay, this is what I want. Theta I said, and I am writing delta. I said theta. Okay. This is clear. For any delta, there exists a T prime between T naught to T naught plus delta. Sorry. T naught to T naught plus. Any delta, there exists a T prime between T naught to T naught plus delta. Okay, such that gamma of T naught is some value, and that is some value. And between this goes to 0. If you want after some n or something, doesn't matter. Okay, it is just this goes to 0 is what we want. So in particular, Py of gamma of Tn will go to sin theta. Take 1 by this, it will go to sin theta. This is for all theta, this is possible. Okay, for any theta. For there exists Tn for any theta. Theta in maybe minus pi to pi. Okay? 0 to 2 pi or minus pi to pi. So this is true. Okay. So now you can see that Py of, but Tn should go to T naught. Thus we have chosen it. So Tn should go to T naught. And then gamma of T naught is some fixed Y naught, which is some theta naught or something. The theta can be anything you like. So this cannot converge. This will contradict the continuity of gamma. Okay. But Py of gamma of Tn will converge to some, that whatever I call it is Y naught, which is equal to sin theta naught something, some fixed theta naught. For any theta, you can do this because it's oscillating so fast. Okay. So this is done. So all I had forgotten is that real connectedness. That's what I wanted to prove. I gave an argument, possibly that is also true. I didn't write it properly, but this will work. Okay. This is the argument. Okay. Now another thing you asked, no, you are the one discussing the zeros of something. Okay. So let us do that also. That also very easy. I somehow got confused. The second one is you take Cn and you have a P is a multivariate polynomial in n variables. In n variables, n complex variables. Okay. Then Cn minus the zeros of that. We call it zeros of P. Zeros of P. When it is multi-variable polynomial, then the zeros can be infinite. It can be uncountable also. This is path connected. That's what we want. So what we did is the following. We took some omega, some z tilde and omega tilde in this Cn minus z. Okay. Then we defined a gamma from C to Cn by gamma of any z is equal to 1 minus z tilde plus z omega tilde. Okay. For any 2 points like this. Okay. Then this P of gamma, okay, is a one variable complex polynomial. Okay. One variable polynomial. So the zeros is finite. Okay. So z of P of gamma, the zeros is finite. Is finite. It's a finite set. So all that. But then I confuse with something. So this implies C minus z of P of gamma is path connected. All I missed is the point, next point. So this implies if we have a path connected set, we have a continuous function. Continuous image of path connected set is also path connected. That is clear. You can write the by continuity, you can get another function. Okay, it's an exercise. Okay. So this implies gamma of C minus z of P of gamma, which actually contains in that Cn, because it can become zero only here in this set. You have removed that set from C. So gamma of this will be contained in z of minus z of C, right? Now this is okay. This is contained in this. So this is path connected. Because continuous image of path connected set is path connected. Okay, since continuous image. Since it is continuous image. Okay. Now we know that W bar and Z bar is element here, which is path connected. So they can be connected by a path, and that's what we want. Okay. They can be connected by a path in this set, which is contained in the big set. So this is the proof. So from that it follows that GL and C is path connected or connected. Okay. So this I wanted to do in the last class, and I got confused. Okay, so now we want to prove. So if you have done with this, if you want to write or something, if you're done with this, I will start a new topic. That is what the topic of this class. Okay. It's called Arzela-Ascoli Theorem. So till now we have been looking at topological properties of metric spaces. Now we are going to do real analysis. Real analysis. Okay. Not the real. Real means the Arzela-Ascoli Theorem. Of course, it involves topology. So the theorem is about determining compact subsets of C of X where X is compact. X is compact. So if we have X is a compact metric space, we deal with metric space. Okay. I mean, we have to deal with metric space because we want to talk about EQ continuity, uniform continuity, and all that. So we have to deal with metric space. Otherwise, it doesn't make sense. So general topology, it doesn't make sense. So it is a compact metric space. Then we know that this is a complete metric space. We have already seen this with respect to what we call the uniform norm, the supremum norm. Infinity norm, this gives rise to a metric, and it is a complete metric space. And we know that in infinite, we have already noticed that the unit ball is not compact. Bounded set need not be compact. Okay, which is the case in finite dimensional or Rn or Cn. Bounded sets are bounded, close to bounded sets are compact. So are relatively compact. Bounded sets are totally bounded. Here it need not be the case. So what happens in the infinite dimension? It's still a function space. Okay, when something is not compact means what will happen is some sort of it becomes unbounded, or because the dimension is infinite, it can kind of oscillate, some sort of oscillation. You cannot, you have to get a subsequence, no? So that will, you have to, if you have a sequence in a metric space, it's compact if and only if it's sequentially compact. So if we have a sequence, you have to get a subsequence which is convergent. So that may not happen. The oscillation may be too much because of the dimension. It may not happen. For example, you take, so example, so units, so in C01, let's say C01, unit bar is not compact. We have already seen this, I'm just recalling. Even bounded sets are not compact. So example is, one example we have seen is x power n. To take the polynomial, n will n. So then x power n will converge to this function 1 in the interval 1 at 1 and 0 everywhere else, right? And the convergence is pointwise. Okay? But this is not, this is a discontinuous function. So the convergence cannot be uniform. So it does not have a uniform convergence. Of course, if something converges uniformly, something converges pointwise, the limit has to be same, of course, by definition. Okay, so it is not uniformly convergent. So this does not have a uniformly convergent subsequence. Another example I said is e power inx, for example, n z are natural number, doesn't matter. This does not have a convergent subsequence. You can do it in two ways. One is you can compute the distance between e power inx and e power imx for n not equal to m. It is easy to compute in L2, whatever the L2 norm, this norm, f minus g whole square in this norm. In this norm, it's easy to compute. I mean, it will be square root 2 here because it will form an orthonormal basis. But then if something converges in L2, then it cannot have a, so because there is a fixed distance, e power in, if you take fn to be this e power inx, right, yeah, because it is 0, 1, you need 2 pi I, correct, yeah. That is to make it, yeah, make it norm 1. Otherwise also it will work, I mean, that is to make it norm 1. Right? You can do it on any interval, yeah, it's better to do it, yeah. That will make it, the norm is equal to 1. So that is what I called as orthonormal basis. So that is one way. If you take it, you use this norm, then there is a fixed distance between them. If you take e power inx, e power imx, if you compute this, then it will follow that when they are different, then the inner product between them is it's not this norm. What is, I mean, there is something called inner product. Yeah, this is the distance between them. What I said is the inner product between two different things will be 0. You can define this to be the inner product, right? We have done all these things. If you have two things, then we can define the inner product like this, okay? 0 to 1. So if you take e power inx and e power imx, this is equal to delta nm. Okay? You can prove this. Just use the integration and you can do it. That will imply that the distance between e power inx, e power imx will be root 2. You can use the, you can write the, whatever I earlier write it, you write it as the square will be there, no? So you write it f minus g bar. You expand it and you will get the answer. It's an easy exercise. Actually, we have gone through this. Okay? So it will not have a L2 subsequence in this topology, in this metric. But then if it has, but it cannot have something in the uniform metric also. Suppose if it is having a subsequence in the uniform metric, convergence subsequence in the uniform metric, then it will have a subsequence in L2 metric also, because uniform convergence, if it is converging uniformly, then you can take the limit inside the integral. Okay, so it will converge in the L2 also. Or you can directly show this. You can compute this. E power inx minus e power imx. You can compute this square. It will be, what is this? This is going to be 1, this square plus this square. I mean, you write it as this times this bar, which will be 2, 1 plus 1, 2, minus 2 into real part of e power inx, e power imx, which is going to be, which is just the cos, no? Cos of n minus m x. Am I right? Which is the real part of that. The basic complex number. Okay. So which is equal to 2 into 1 minus cos n minus n, which is going to be sin n minus m by n minus m x by 2 square. Okay. And you can see that in this interval, the maximum value will be attained. Okay. And this will be, so if you take the supremum over x, then the norm of this e power I m x minus e power I m x, the norm, supremum norm will be 2. The square, I mean, will be root 2. Okay. So there is a fixed distance between this function and this function. This cannot have a convergence subsequence. Okay. So I mean, what we are saying is this is not relatively compact. This is okay. So what we want to prove is something called Arzela-Ascoli theorem. To prove that, we need another notion, which is called equicontinuity. We have seen uniform continuity. It is just a generalization of the equicontinuity for a class of functions. Okay. So this is the definition. Which one is? Not equicontinuous. Arzela-Ascoli theorem is generalization of Heine-Borel theorem. Heine-Borel theorem, which says that closed bounded sets are compact in Rn. Here, closed bound and something more is needed for it to be compact in CFX. Okay. I will tell you why. Okay. After this. So a function space. This is a collection of functions in C of x, where x is compact. X need not be compact. Let's say x is just a metric space for the time being. Of course, we are going to work with compact. Is said to be or is equicontinuous if given epsilon greater than 0, there is a uniform delta. Uniform continuity means the delta should not depend on the points. Okay. Equicontinuity means usually equicontinuity, there are many definitions. Equicontinuous at a point and uniformly, there are many definitions, but I want to use this definition because we are not going to use other definitions. Okay, we need not list so many definitions. So I am calling this as equicontinuous. Okay. So it is called equicontinuous if there exists a given an epsilon, there exists a delta, which is uniform for all points and also for all functions. This is a collection of functions. So this is uniform for all functions. There exists a delta such that f of x minus f of y is less than epsilon if d of xy, I mean, this is taking values in complex number or real number. Okay? This is over R or C. This d of x is over R or C. It's a vector space over there. Okay? And if d of xy is less than delta. So this is the definition of this is just a generalization of uniform continuity to a collection of equicontinuous. If you have a single function, then it is equicontinuous. Singleton, f is, if the class is just one function, then it is equicontinuous if and only if it is uniform continuous. Okay? In this definition, the general definition is this. Okay. So this is the Arzela-Ascoli theorem. So let's see example of this. Let's see example of uniform continuity and complex. Example. So if you have a single function from C from f is a function in C of x cross y. Okay. Single continuous function. Okay. Then I define this function, this class. At f x equal to fix a x, fx at y equal to just a perfect y. Okay, let's take this to be compact. Yeah. Because we don't want to confuse. I mean, f is continuous, so it is uniform continuous also. Okay, we want to use that. Okay, so otherwise we need to think about that. I mean, otherwise we have to impose another condition, f is uniform continuous also. So then this collection fx, x in x, is equicontinuous, which is clear, right? It's a trivial example. This is clear, right? F is from x and y are compact, so this is uniform continuous. So I define a collection indexed by x, fx. Okay, this collection is equicontinuous. If you use the definition, you just write the definition, it is just formed, right? it is just the same thing as uniformity. Second example is, this is more important. You take, the C1, we have defined C1. So all those function f in C0, I mean, this is as a subspace of C01. Okay. F in C1, 01, and norm of F1, F prime in infinity is less than. I mean, this is compact. This is equivalent as a subspace here. Okay. Why I am saying a subspace here, it will be important when we state the theorem. Okay? It will be clear. Anyway, this collection is equicontinuous. I am saying that you take all those f in C1, 01, such that the derivative f infinity is less than m. That's the only condition. Okay? So this collection is equicontinuous. Why is this true? You want to talk about f of x minus f of y. It will be clear what you. This is equal to f prime of z for some z between x and y, such that minus x minus y. Okay? And f prime is less than m, so this is m into x minus y. So given an epsilon, you can find delta when this is the delta should be epsilon by m something. Okay, so take delta equal to epsilon by m. Okay, that will work for all f. Okay? So this set is equicontinuous, right? Okay, this is fine. This is easy example. This will not work for just norm f infinity is less than or equal to. It will not work. Of course, we have seen, we have counted that. Okay, so let's state the theorem now. Theorem is, we need one more condition. That's what it says. Yes. There's something f, maybe I'll call it k, x is compact. Okay, I will make some remark. Sorry, I will make some remark about equiquantity. So the remark is the following. This is a remark. I'll make the remark and the proof will be easy. So if we have some fn which is equicontinuous, a collection of sequence of function which is equicontinuous, and f1 converges to f pointwise. F1 in C of x need not be compact. Then f is continuous. Pointwise convergence need not imply the limit is continuous. But when it is equicontinuous, it will follow that it is actually continuous. And the proof is easy, right? You want to talk about the continuity, you want to talk about the continuity, you want to consider this. But this is equal to limit of f1x minus f1y. Okay? And given delta somewhere, we can make this, each one of them less than epsilon uniformly. So the supremum will also, limit will also be less than epsilon. Limit will be actually less than or equal to epsilon. You have to take something more than epsilon. Maybe you can take this is less than 2 epsilon if you want. You can work with 2 epsilon. Okay. So, I mean, whenever you take limit, the inequality may become less than or equal to. So you may have to take something slightly bigger. So another remark is, if fn, so this is in C of x, where x is compact, okay, and it is equicontinuous, okay? And fn converges to f pointwise, implies fn converges to f uniformly. It will follow from the theorem. Arzela-Ascoli, whatever we are going to prove. I will write it as a curve. If you have a collection of functions which are equicontinuous, and suppose they converge pointwise, then the limit is also, then the convergence is actually uniform. This need not happen here. Okay, so this is for x in compact. X should be compact. So why is this true? We will see. It will follow immediately from this Arzela-Ascoli theorem. So here is the theorem. Arzela-Ascoli. So you have a K which is the subset of C of X. X is compact. Good. I mean, X. A K, so X is compact, but K is a subset of this function space. This is compact. If and only if K is closed, of course, compact means closed, and of course it should be bounded. Bounded means it's not functional, it's uniformly bounded, right? It is bounded subset of C of X. This bounded means norm F infinity, F in K. This supremum should be less than. This should be fine, which is uniformly bounded. Here bounded by bounded means bounded in norm infinity, which means it is uniformly bounded. Okay. And equicontinuous. The collection K is equicontinuous. That's all. If it is equicontinuous, this is only one more condition, equicontinuous. Okay. Now you consider Heine-Born theorem, you ask for it, no? So this, if you take a subset of K, this Rn is actually a continuous function on this n set, 1 up to n, right? All functions, but it's finite set, so it is continuous, right? Okay. So if a subset is, so if you have a K contained in Rn, it is automatically equicontinuous. So if it is closed and bounded, then it is, so it is some sort of, I mean, you need not consider like that, but some sort of generalization of Heine-Born theorem. Closed and bounded subsets of Rn are compact. But they are automatically equicontinuous if you consider as functions on 1 to n. They are anyway continuous. This is a finite set and it's always continuous and it will be equicontinuous also because you can work it out. Okay. So it's because of this is one way of looking at the proof. Okay. So suppose this is one way, the easier way is compact. Of course, it is closed bounded, that's clear. Only we have to prove the equicontinuity. Any compact set is closed and bounded. So we have to prove the equicontinuity. So how do you prove equicontinuity? We have assumed K is compact. In particular, K is totally bounded. Okay, so given epsilon greater than 0, particular this implies K is totally bounded. You remember the definition of totally boundedness. Given epsilon, you will find what is called an epsilon net. Okay, there exists F1 up to Fn in K such that K is contained in union of I equal to 1 to n B of Fi epsilon. Right? This is the totally bounded. Okay. Okay. Now for each of those Fi, you choose a delta I. To take the infimum of those delta, that delta should work for the equicontinuity statement, the definition of equicontinuity. So let delta I greater than B such that x minus dx minus dxy less than delta I implies f of x, fix minus fiy, fiy is less than epsilon. Okay. You choose a delta I like that. Okay. For each fi, they are all uniformly continuous. They are, okay. This is true. Now delta equal to minimum of, there are only finitely many of them, delta 1 of it, delta n. Okay. Now it's clear. Now if dxy is less than delta, of course, that means it's less than all delta I, and let f is in K, implies f is in some B of Fy epsilon for some I. Okay. Because that's the union, some I. Now we know that f of x minus f of y epsilon by t less than or equal to f of x minus fix plus fix minus fiy plus fiy minus f of y. So f is in the open ball. It is uniformly approximated by this fi. F is uniformly up to epsilon. It's approximated by this fi. So this and this for different x and y. This and this is less than epsilon. And this is by the uniform continuity of phi. This is less than epsilon. I mean, that's why we have chosen the delta I. So this is less than 3m. And x minus dxy is less than 10. Okay. So it follows. So this is direct. This is the easy part. So compact implies the equicontinuity. So now we prove this thing. Okay. So let K is closed, is closed, and what is the other one? Bounded and equicontinuity. So close this, of course, close this we are going to use. We know that compact is equivalent to closed and totally bounded. So we don't use the closeness. Closed is closed, and we use bounded and equicontinuous to prove that it is actually totally bounded. Okay. So we prove K is totally bounded. Okay. To prove totally boundedness, we have to get some open balls such that union of those open ball is union of, I mean, given epsilon greater than 0, we want, this is what, given an epsilon greater than 0, we have to find open ball such that it covers the K. There are finitely many of them. Now it is F1 up to F1. Given an epsilon greater than 0, we have to find finitely many of them in K such that open ball around those finitely, epsilon open ball around that should cover that. Okay. Instead, what we will do is we will find, we will be clear later. So we will get some set, finite set, which will cover them in epsilon, maybe some 4 epsilon, 5 epsilon, doesn't matter. We can take it epsilon by 4 and work with that. Okay. So select epsilon greater than 0. Then we consider and delta. So and delta greater than 0 be such that this thing, which is given by this equicontinuity, less than delta implies f of x minus f of y is less than epsilon. Okay. That for a given epsilon, you take a delta such that which is given by the equicontinuity. Now choose. What we do is the following. So given epsilon, you have got a delta. Now for that delta, which is in, I mean, which is related to the distance in xy, this x is compact, so it has to be totally bounded. You choose x1 up to xn in x. Okay, finitely many of them. On the other hand, here this given epsilon, this range is also compact because it's bounded. The whole thing is 0, 0 something. It's a bounded set in either in complex plane or in real plane. The range of all those f is inside something. Range is also bounded. So you can, that's also totally bounded. For a given epsilon, you can find y1 up to ym or something such that which is for the totally boundedness statement for the range of this all this f. Now you find all those constant function. I mean all those not constant function. All those this finitely x1 up to xn, y1 up to ym. You take all those functions. There are finitely many of them from finite set to finite set. This is x. X is by totally boundedness. You have x1 up to xn, so that this covers this. This is the range of whole of K. Okay. Here you have y1 up to ym. Okay. You consider all functions from this set. I mean, this is whole of H. This is whole of this range V of 0m, where f of x is less than m for all f in K for all x in x. You have got a m like this because we have assumed that it is bounded, so we have got a m like this. Okay, this is just b0m. Okay, this is b0m. That is x. Now we have got finitely many of them such that delta ball around that covers this. Epsilon ball around that covers this. Then you consider functions from this finite set to finite set. Okay. and you will using this, you will find open ball for that. Not open ball, some set which has finite diameter. And if you have set with the finite diameter, you can choose anything in that and take the ball around that. That will be an open ball, right? Anyway, we'll write it. We'll write all that. Usually there are proofs which usually use the sequentially compactness and other things. I mean, there are many proofs. This is a very nice proof by Kumaresan. In his book, you can read. I like this proof. It is just totally boundedness. You use the totally boundedness of this, and you get a constant function. So let A equal to all those functions. So maybe I'll write again. So okay. So let x1 up to xn in x be such that x is equal to union of b of xi delta I equal to 1 to n. Okay. And m be such that f of x is less than m for all f in k and x in x. Because it's bounded, this is possible. Okay. Now choose. You know that this open ball around, I mean, this m, that is bounded. Choose y1 up to ym in B0m, contained either in real line or complex plane. Okay. This 0 is the actual 0, either in complex or thing. So is 0m, such that B0m, which is compact, of course, contained in B union of B of yi epsilon I equal to j equal to 1 to m. Okay. So now A, B is a set. All those functions from this finite set x1 up to xm to y1 up to ym. There are m to the power n to the power m. No, m to this cardinality of A is finite. That's what we need. N to the power m. No, n of doesn't matter. N to the power m to the power n, n to the power m. Okay. You have to choose for each one of them. You can choose it in m base. This can be chosen in m base. Everything can be chosen in m base. So it is m to the power n. M to the power n. Doesn't matter. It is finite. That's what we want. Okay. For us, there are finitely many functions. That's what we want. Okay. Okay. Now you define this A for alpha in A. Define u alpha to be all those f in K such that f of xi minus alpha of xi. Alpha is this from this set. This is less than epsilon. You can define it. Epsilon is fixed. Okay, we are working with epsilon. Okay. So first claim is diameter of u alpha is less than or equal to 4 epsilon. This is claim. And union of u alpha, alpha in that A, covers the K. These are the two things. So once the diameter is 4 epsilon, you can take any element here. You can take an open ball around that. That will be maybe slightly more than 4 epsilon. That will cover the whole of u alpha. Okay. Then you will get finitely many of them, and then you can write it. So okay, it's clear. Okay. So this proves that this is totally bounded. You can write this as you can write a slightly bigger ball, and you can get an open ball. Okay. So it is this statement and this statement we have to prove. So so first K is contained in u alpha. So F is in K. Okay. Then define and f of xi f of xi is going to land in that open ball 0m. I mean, it's going to be bounded by 0m. So it is going to be in one of those balls, b of yi ball. So and f of xi is in b of yi epsilon. It's going to be in one of them, right? So it's going to be in yi epsilon. Then define alpha of xi equal to yi. If this is the case, then define like that. Okay? Then it's clear. Then f of xi minus alpha of xi is less than epsilon by definition. So this implies f is in u alpha. So given any f in k, f is in u alpha for some alpha. Okay, you get the so this statement is true. Okay, so this implies union of u alpha alpha in a contains k. Okay? Something is in k, it is here. Okay? Now we want to prove the other one. So if f and g are in u alpha, we want to compute this norm, supremum norm, f minus g, f of g x minus g of x. I mean, you use the triangle inequality several times. Of course, I said 4 epsilon, so it will be 4 times. So this is less than or equal to f of x minus f of x, yeah, f of xi, f of xi minus alpha of xi. Yeah, alpha. They are in u alpha. Okay, so they are in epsilon distance between alpha. F of xi and alpha of xi. This is true for g also by definition. G of xi plus g of xi minus g of x. So this is less than 4x. So the diameter is less than 4x, is less than or equal to 4 epsilon. So if you want, you can take a slightly bigger ball. You get and take an element here in that u alpha. Those that will give an open ball, and those open ball will cover k. So k is totally bounded. Okay? So this implies k is totally bounded. That is true. Okay. Okay. So we have proved Arzela-Ascoli theorem. So first corollary is f in C01 such that norm f infinity. Remember, this is a compact set in this f prime infinity less than or equal to m is compact. Is compact. It's closed here. Whenever you have less than or equal to, it will be closed. Okay? So it is closed. It's compact in this. It's clear because we already proved its equivalent. It's closed. It's bounded. In this condition ensures it's bounded. All those functions are bounded. The set is bounded. This is implies it's closed, and this is equicontinuous here. So this is compact. Second corollary, as I said, Fn contained in C of x, x compact. Okay. Then Fn converges to F pointwise compact and this is equicontinuous. Fn equicontinuous and Fn converges to F pointwise for all t next. Then Fn converges to F uniform. Can you give me can someone tell me a proof of this? There is some subtlety in this. The point is Fn is equicontinuous. So this set Fn is sequentially compact. So given Fn, you will get a subsequence. You have something pointwise convergence. Given Fn, there will be a subsequent which converges to F. So why is Fn converges to F uniform? This is a subsequent convergence uniform. Is a quiz. 5 marks, 10 marks. Depends on the difficulty. Come on. You understand the point? Fn is converges pointwise. Fn is equicontinuous. So by this Arzela-Ascoli theorem, Fn has a subsequence which converges uniformly. And Fn converges pointwise. The claim is Fn converges F uniformly. Fn itself converges uniformly. Okay. Have you seen this fact? If you have a metric space, if you have a sequence, okay, if every subsequence of the sequence is a further subsequence which converges to a limit, the limit should be same for all these statements. Yeah, you have a sequence. For every subsequence of the sequence, there is a further subsequence which converges to some particular element. Then the whole sequence will converge to that. Of course, that's what I said. That limit is fixed. So then that sequence converges to that. Okay? This is in any metric space. This is a theory, I mean, fact about metric space. Now you have what is specific about it? Subsequence has a subsequence. That's what the statement. The statement itself is you can choose. Okay? You have a subsequence. If you have a subsequence, there is a further subsequence. You can choose some subsequence. There may be several. We are actually proving that the sequence itself is convergent. So subsequence cannot be unique. Okay. Huh? Yeah, it's an exercise. Yeah, you can prove it. It's not difficult to prove. It's a first class. I mean, first two classes. No, it's an exercise. You should have given it in the first two classes. Okay. So it's an easy exercise. Okay. You use that, it will follow. Now Fn converges. Fn is equicontinuous. So given any subsequence, that is also equicontinuous. So that is a further subsequence that will converge to some element. But then that cannot be different. It has to be F because point-wise convergence ensures that is same. Because of that, this will go to that. Huh? This Fn, you take a subsequence of this. That will have because that is equicontinuous, there is a further subsequence that will converge uniformly. And the limit cannot be different because point-wise it converges to F. So it has to converge to F. So every subsequence has a further subsequence which converges to uniformly in F. Okay. So Fn has to converge to F uniform. Possibly, if you have remembered that, one of you would have said. Okay. I mean, you remember this statement, possibly this sequence, further subsequence. So what else? There are several applications to this Arzela-Ascoli theorem. If you are an analyst, if you are going to work in mathematics, you do analysis, function analysis, or differential equation, you will encounter this many times. Okay. So, for example, there are something called. So, is there any easy examples? So, okay. There are many things. First, one application example. So, let us take a function, small function. I mean, not small function, small k. Okay? Small k is a function from, let us take it 0, 1, otherwise you have to integrate that to be measured. It's a two variable function. K is a two variable function, continuous function, 0, 1 cross 0, 1. Okay? Now define, this is a linear operator. You might be knowing what it is. Okay, I don't need capitals. I use Tk from C01. This is a function space. This is a metric space, complete metric space, which is actually called Banach space. Okay? C01 to C01. Okay? I define this Tk by Tk is to take a function from here to a function here. Okay? So Tk acting on a function should be a function on this. I mean, it's the same thing. Okay? So at x, I have to say what it is integral 0 to 1 k xy of y dy. Okay. Tk of f at x is kxy f of y dy. This at x gets integrated. Okay. This x is fixed and the integration is respect to y. Okay. So this is one variable function. So this is what is called integral operator. Okay. Then this is what is called, I mean, this operator, the property I'm going to describe is what is called a compact operator. By compact operator, we mean the following: it takes bounded sets to compact sets. Okay. In particular, Tk f with norm f less than or equal to some m, okay, is compact. Norm f is a compact subset. Okay, maybe I take the closure. It need not take closure to close set, so I take the closure. I mean, linear operator need not take closure to close set. Okay, so in infinite dimension. So this set TKF as f varies over this ball, okay, m ball, or you can take one if you want. Okay. Then this is a compact set. Okay. So all we have to prove is this is relatively compact. This is what I'm taking the closure. So this is relatively compact. So all I have to prove is it's totally, I mean, it's equicontinuous. By Arzela theorem, we only need to prove it's equicontinuous. Okay. So let's just see why it is equicontinuous. So what do you have to prove? We have to get a delta such that TKF, these things, TKF of x minus TKF of y or something. So because y is inside the integration, I take x1, x2. Okay, x1, x2, for x1, x2 in x. Okay. I want to talk about Tk of f at x1 minus Tk of f at x2. I want to consider this, okay, modulus of this. Okay. I have to take the supremum also later. Okay. So this is equal to integral of k x1 y minus f of y dy minus again k x2 will come. Okay, this modulus. So I will take the modulus here. So then k x2y will come. Okay. Okay. That's the same statement. This is less than or equal to, I mean, you know that mod can be taken inside, which is actually kind of triangular inequality. Because integration is sum, you can take it inside. Inside, this is 0, 1, 0 to 1. Mod of k x1 y minus k x2 y times f of y, mod f of y dy. But mod f of y is less than m. Okay, so this is less than or equal to m times 0 to 1 k of x1 y minus k of x2 y dy. Now k is continuous. Given epsilon, we are given an epsilon, you can find a delta such that this difference is less than epsilon. Okay? Yes, k is uniformly continuous. And that is, I mean, irrespective of y and all doesn't matter. Okay? So this can be made less than m times epsilon by m if you want. But, and the integration is between 0 to 1. The constant will become less than epsilon 1 if x1, if b of x1 y x2 is less than some delta. Okay. Delta can be chosen such that this happens. Okay. So we have proved that. So that is equicontinuous and that. Any question? Okay. So I have 10 minutes. I will give you another application. Anything else? I will ask one of the TA to do some differential equation application of this. So there is something called Riemann mapping theorem. I'm not going to talk about it. You have not done complex analysis yet, no? So, but you know Cauchy integration formula? Cauchy integration formula. Okay. So which says the following. If you have, holomorphic function. Holomorphic function. Okay? Holomorphic function on complex plane. Holomorphic. I thought you don't prepare for IIT and all that. I mean, you have not heard holomorphic function. Functions which are once differentiable or infinitely differentiable in complex variable. And it's holomorphic function, which you can write it as a power series. Anyway, you will learn it in complex analysis plus, but I thought you will know this more. Okay. You heard it in +2? No. Yeah, heard of it. Yeah. That's all. Not a serious theorem. So if you have any holomorphic function, this is what is called Cauchy integration formula. I am not going to prove it. You will see this later. Okay. You'll see this later. Cauchy is the Cauchy-Schwarz and the Cauchy sequence, that Cauchy. Okay. I mean, the name, that person. Cauchy integration formula. Maybe not because there may be some other person. Anyway, Cauchy integration formula is the following. F is, so always whenever you talk about holomorphism, you have to take an open set, open connected domain. Let us, for example, let us take the, okay, let's, F is holomorphic. F is a holomorphic function. Holomorphic means it's infinitely differentiable. Okay? Complex functions, if you can differentiate once, you can differentiate infinitely. Okay? So it's because of that. Holomorphic on some omega contained in P. Okay, this is open. Open and are simply connected domain, whatever. You take connected also. Okay, open and connected. Okay, connected. Okay, so that it is path connected. So then the domain is like this. Okay, and you have a point somewhere, some Z0. You have a point in that this. Then you can take a curve around this. You call this curve gamma. Okay. Then if you integrate this gamma over this, that will be 0. But that's not the point. F of Z0 is equal to, this is the formula. This is just the curve I am taking. The integration is over curve. The curve will be given by one parameter, right? Curve is a, okay? So it will be, I mean, you can take, you can actually get a function from 0, 1, interval 0, 1 to here, such that the end points, the value is same. Okay, that's a closed curve. So integral over this curve, gamma, okay, f of z by z minus z0. This function is not holomorphic because z minus z0. This is not a holomorphic. But on this makes sense because z0 is somewhere inside. Okay, on this curve, it makes sense. Okay, this is Cauchy's formula, Cauchy integration formula. Why I am saying is the following. This is the theorem. This is just to, this is not part of our course. I want to tell you how Arzela-Ascoli theorem is used. Okay, maybe I will not give a full proof in 5 minutes. So if you have a Fn, let us take the unit disk, just the unit, not the line, open ball of radius 1 around 0. Okay, Fn is holomorphic in B0, 1 contained in C. Okay, is a holomorphic, is a collection of holomorphic such that it is bounded. See, we know that continuous function need not have a uniformly convergent subsequence, right? But if it is holomorphic, and even continuous function, continuous sequence of continuous function which is bounded need not have a convergent subsequence, uniformly convergent subsequence. If it is holomorphic, if it is bounded on all compact subsets, omega is not compact, it is open, need not be compact. Compact subsets means all closed disks, okay, inside there. Okay. So Fn, so for all K compact contained in omega, I said close this, okay, this is omega. You can actually write it for any omega, it will work. Any connected, open, connected domain, you can do that. Compact, for all compacts, there exists a Ck, a constant greater than 0, such that Fn Z is less than Ck for all Z in K. It is bounded on all compact sets. Okay. Then this is the theorem. This is called Montel's theorem or something. We use this theorem to prove Riemann mapping theorem. This is not Riemann mapping. Okay. Then there exists a subsequence of Fn which converges to a holomorphic F. If you have a collection of holomorphic functions, then which is bounded on compact sets, then there is a subsequence which converges to a holomorphic function uniformly on compact. The convergence will be uniform, but uniformly on compact sets. Omega. This is the theorem. The proof is easy. The proof is you have to prove. So you have proof is not exactly easy because I'm not going to give all the detail. What happens is you restrict the Fn to compact subset. Okay. Then that will have a subsequence which converges to something which is holomorphic. Okay. That will have a subsequence which converges to some continuous function. Okay. Okay. Then, but then for each compact set, you will have a subsequence. The point is you have to choose one single subsequence for everything. That can be done. Okay. I just want to show you the Arzela-Ascoli, how it is, this is applied. And another thing is, another statement is Fn converges to F continuously and uniformly and compact subsets in a domain, then the limit is also holomorphic. That is another statement, which I am not going to prove. Okay. The only thing is how to apply this Arzela-Ascoli theorem, how to get a subsequence. To prove there is a subsequence, all you have to do is you have this. This is the big disk. Okay. You have to prove that this is on compact set, this is equicontinuous. Once you prove equicontinuous, there is a subsequence which converges uniformly. Okay. So by that you take a subsequence consistently for all compact sets. That will give a single function F such that it converges uniformly in compact sets to that F. Then it will follow F is holomorphic, and that's all. That's what we want. Okay. So now if we have 2 points, Z1, Z2 here, then you can take this something of say radius R, and maybe you can take this radius R. And then you can take another thing with radius capital R, okay, around 0. Okay. Now we want to consider this f of Z1 minus f of Z2, right? Which is actually you can integrate on this bigger circle. Why I am taking this R will come. I mean, so because you want both this to be contained in a smaller thing. Okay. So f of Z1 minus f of Z2, which is equal to integral over gamma. Gamma is the bigger circle, so which is that all those z such that norm z equal to r, mod z equal to r. You are integrating over this f of z. See the z1, it's same. It's similar to this proof. The variable z1 and z2 that will appear at the bottom now because of Cauchy integral formula. Okay, z minus z1 minus f of z minus z minus z2 dz. Okay, and you need the mod. Okay, you have to take the mod and take the mod inside and all that, and f is less than mk or something, so there is a m, f will go away. Okay, and all you have is the integral over z such that mod z equal to r, 1 by z minus z1, 1 by z minus z2. To take it to the top, you will get mod of z1 minus z2, right? Yeah, mod of z1 minus z2 into z minus z1 into z minus z2, right? Okay, z1 minus z2 mod of z1, that's a number. M is a number, so you can convert this to polar coordinate or something. I mean, this circle is determined by theta. Theta between 0 to 2 pi. So this integral will be maybe less than or equal to, because I want to. Okay, it's equal to, I think, integral 0 to 2 pi and that is R, no? R times dt, d theta. This can be written as e power I theta, R times e power I theta minus Z1 minus R e power I theta minus Z2. Okay. You can change a variable or something. Okay, you will get this. Now R e power I theta, which is here, something here. Okay. Z1 something here. Distance between them is greater than this distance. So 1 by the distance is less than this distance, right? So this is less than or equal to 0 to 2 pi, I mean some constant time, 0 to 2 pi. And R everything goes to that constant, d theta by. So this is less than or equal to that R minus R. And R minus R again. Okay. So this is just a what do you want to do? If times Z1 minus Z2, I shouldn't take that. Times Z1 minus Z2. Some constant times Z1 minus Z2. Now you can do the equivalent. Z1 minus Z2 is F. We started with F of Z1 minus F of Z2, which is some constant times Z1 minus Z2. This is all constant. Z1 minus Z2, which does not depend on Z1 and Z2. It is constant. Okay. So given epsilon, you can take something epsilon by this constant, which is okay. So this is another application.